Welcome back, dear friends. Welcome to Engineering Ninja. We are here with module 2 of ABAQUS, that's Advanced Module. So, in the very first video, in today's video, we are going to simulate tensile test of a steel rod. How we do in the experiments. And here we are going to simulate the same using ABAQUS. The specifications of our sample are shown here. The gauge length of our specimen we are taking as 100 mm. You can refer to various, there are various codes for tensile testing on metals. So you can refer to IS 1608. There are other references also. So here we are using the gauge length of 100 units. That's we are using 100 mm, and the dia for circular this cross section will be 20 mm. We are using a circular specimen, and with grips, the grip lengths we have the grip dimensions are 30 mm by 20 mm. 20 mm is the depth or the height, and 30 mm is the dia of the grip. And we'll be using units Newton mm, since we know it's ABAQUS is unitless, so we have to be consistent with the units. So I'll be using a Newton mm system of units, and this is the specification. So let's get started. Okay, so we are in the GUI of ABAQUS. So we are already in the path module. So let me close this. Here is the path, and let's create a path. Let's name this as steel rod. I need to create a steel rod, deformable solid. Okay, done. Now let me create a cross section of that steel rod. Since that's circular, let's go to the circle, create anywhere, create circle of any dimensions. Now go to add dimension. Dimension here is 26 mm, but since I have a total diameter of 20 mm, so my radius will be 10 mm. So this is the cross section of my rod. Done. Now it says the depth, that means the gauge length of my steel rod. That's nothing but 100 mm. Okay, so we are done with the gauge part of our specimen, but I need to create the two grips, right? So let me go to create solid extrude. I want to create an extrusion on this side and that side. First, let me create an extrusion in this side. So let me select this surface. Any edge could be right, left. Since this is circular, it doesn't matter. So go to the circles, create a circle, place it here of any dimensions, go to the dimension, and let me mark these. It's 8.08, but my total diameter of my grip, if you can see, is it's 30 mm at the bottom. So my radius will be 15, right? 15 mm. Escape. Done. So what should be the depth of it or the length of it? So it's 20 mm. 20 mm. Right. So extrude direction is outwards. It's correct. Okay, I've created a grip on one side. Now let me create a grip on that another side. So again, go to create solid extrude. I'll rotate it. I'll select this plane. Now again, go to circle. Of these, it's almost there, but I can check the dimensions here. 14.79, so it has to be 15 is the radius, correct? Done. So again, it's outwards. It is depth is 20 mm. Done. Okay. So if you see, we are able to create our specimen along with the gauge as also the grips. So what is the next part? Next part is the property. Let's go to the property. Let's say the property name is steel density. Please refer to my older videos wherein you'll learn what should be the units of the density when we are using Newton mm. So it is 7800 e power minus 9, rather minus 12. 7.7800 e power minus 12. Understood? Now, elastic properties I'll give. Elastic properties of steel. Since we are using Newton mm, Young's modulus has to be in megapascals. So it is 2 into e power 5. 2 and 5 zeros. Poisson's ratio, let's assume as 0.3. Now, I need to give the plastic properties. And here, I'm idealizing the material as elastoplastic, as you can see, with strain hardening. The yield strength I've assumed is 415 and the ultimate strength is 500, right? Here 0.1 I'm assuming is inelastic strain or the plastic strain. It is the total strain minus the elastic strain. So I need to put this inelastic value of 0.1 corresponding to 500. This is not the total strain, please remember. So at yield stress of 415 megapascal, I'm assuming a plastic strain of 0. There's no plastic strain here, right? Now I'll add another row after 500, and I'm assuming a plastic strain of 0.1. So from here to here, we have a plastic strain range. So this part will be utilized, this elastic part will be utilized in this region, and this hardening part will be idealized by the plastic properties. Okay, let's save. Now I need to create a section. It's a steel section with steel properties. There's only single property created. So, okay. Now I need to assign section. Select the regions to be assigned section. This is the region. Done. Which section do you want to assign? Steel. That I already defined. Okay. Now I'm done with the properties. Let's go to the assembly. I need to take this into the assembly, steel rod into the assembly. I have taken it. It's very much fine. Right. We are here. Now go to the step. So go to the step, create step. Let's static general. This is nonlinear geometry. Let's keep it on. This sometimes removes the instabilities or large displacements. We have created a step. Let's give a time period of total 10 seconds here, since we are going to give load, my load as a displacement. I'm going to give a displacement control load for 10 seconds. So let's put 10 seconds as a time period. I'm done with this. So this is the field output. Field output means what is the result? What are the results that you want to have? It's already there: stresses, strains, displacements, forces, contacts. Okay, let's have it like that. Similarly, energies, history in the history output. What kind of energy? All strain energies, dissipation energies, and all. So I'm done with this. Let's create an interaction. So what I'll do is I will in the interaction I will put a reference point at the top. Reference point. I'll put a reference point at the top node. What I'll do, I'll couple this reference point with the tops, this grip where the load's getting applied. Coupling, done. What is the control point? Control point is this reference point. Okay, done. And what is the constraint region type? I want to couple this reference point with this top grip surface. Let's create, okay, whole surface. Fine, done, done. The advantage of using this couple is when I'll be plotting force displacement, so I need not select all the nodes and then taking the sum of the forces on all the nodes and then then plotting them. So automatically all the forces on the nodes will be coupled at this reference point. Okay, now let's go to the load. I'll go to the boundary conditions, create boundary condition. Let's name it as a bottom. I'll fix it at the bottom. So let's fix this whole surface at the bottom, right? Done. And caster, it's the rigid constraint or the fixity. And now I need to pull it at the top. So this is the top boundary condition, wherein I'll specify to this reference point. Now I need to go to, again, displacement. I need to give displacement at the top. Select this reference point, done. In U3 direction, in positive U3 direction, let me give it as a unit as a 1, and then let me create an amplitude here. Amplitude at 0 time, it is 0 amplitude. Let's say at 10 seconds, it's 5 mm. It's a bit faster rate of loading have created, but since we are using static general, it will not affect our results a lot. So it might create some instabilities, but let's see. At 10 seconds, I'm choosing 5 mm as the displacement. So this is a triangular kind of a variation, rather linear. It's a linearly increasing load from 0 to 5 mm. Done. I'll select this amplitude. Done. Okay, now it will be pulling it at the top. Now create mesh. So dependent paths cannot be edited, or so we need to go to the path. We need to use mesh size of let's say 2 mm. The selected regions cannot be meshed automatically using assigned element types. They must either be partitioned or assigned a tetra shape. We can do two things here. Since we have not partitioned these grips from the main gauge, either we need to partition them or we need to change the element type. So let's partition them. That way you'll also learn how to create partitions in case of circular specimens. So let me create a datum plane. Create datum plane, and the plane will be XY plane perpendicular to the axis of this member. XY plane 0 0. Okay, it's here, it's correct. Now let me partition it. Go to the here partition using cutting plane, partition using datum plane. Okay, select the datum plane. This is the datum plane. Create partition. Okay, it has separated it. Now I need a datum plane at here also at the bottom. That means I need to go to the create bottom datum plane, XY plane, 100 mm offset. Since see here, it's created a datum plane here. Now partition using datum plane. This is the plane. Rather this is the cell I want. Okay, cell I want to partition. This is the datum plane that I want to select. Create. Now you can easily use the mesh size of 2 mm mesh. Yes, mesh. We could have also we could have you know created a plane. No, one what I want to emphasize here on I want to so we could what we could have done here another thing. So what we have done here is we have meshed it using our regular meshing techniques. But since we had to partition it, without partitioning, we needed to change the mesh type to tetra here. Mesh control, we had to select this, then we needed to go to the tetra hedral meshes. So that was another way. So we are fine here. Let's go to job, create job. Let's name it as tensile test. Submit. So we'll be able to monitor it over here. Okay, it has started running, so there are no errors for now. Okay, so we are done with the analysis. Let's go to the results. Let's click on this plot contours. Now we'll go to the last step. Yes, we have exaggerated the results a bit so that we can observe necking. If we animate this, you can see the animation of the results. This is the plastic strain. You can see one messes stresses also. See, if we go one by one, step by step, one messes stresses, and the deflection. If you see the total displacement, it's 5 mm is the total displacement that we had initially given, and it has stopped there. So let's plot stress strain profile of the graph or the force displacement, and it should be bilinear as idealized in the beginning. So let's go to the operate on XY data, rather XY data field ODB field output. Select a unique nodal is selected. In the reference point RF3, okay, that's the force in the third direction and the displacement in the third direction we have selected. Go to elements, click on node labels or node sets. There's already one node set at the reference point. So if we plot these, we're getting a plot something like this. These are plotted separately. Force, the blue, rather the green color, and displacement, the blue color. But if we want to combine them, let's go to the XY data, operate on XY data. We already have these two here. So what we need to do is go to combine, double click this, then double click on this. Force, first displacement, then force, and then plot. So here is your absolutely directly defined. This is the bilinear, this is linear part, this is that strain hardening part. Or you can see at ultimate deflection is 5 mm. And you can also plot stress strain graph. Let me choose a single point at the anywhere at the center or at the bottom. Let's see, the plastic strain is maximum at the center. I'll choose any element. Let me first delete this result, create ODB field output. When you are plotting stress versus strain, you need not go to the unique nodal. You first check them off. Displacement, you go to the integration points. Stress. Let's plot one messes stress with plastic or maximum principal strain plot. I have not yet selected any entity. Edit, select any point at the center. Done. Plot. Again, it's a similar kind of a behavior, but let's uh, let's create xy. Let's combine them. Operate on xy. We have these two here. Combine. Strain, stress, plot. So here is your stress versus strain plot. At absolutely 415, you have a yielding point, and then it's then not reaching the ultimate uh, stress. Or that's the 500. Reasons could be many, because it's not reached the point one strain. Ultimate strain I have given is 0.1. So at this, it's not yet reached 0.1. So that's how. But the idea here is the stress strain plot you're getting is exactly bilinear as we had idealized. You can now play with the meshes, make it even finer, and also increase the simulation time so that it reaches the ultimate strain that we had given. Increase the rate of the rather increase the displacement in the input, and also increase the simulation time so that it reaches the ultimate strength. So this way we can simulate the tensile test of our steel rod, and you also learned how we can extract the data, that is the stress strain or the displacement, force displacement curves out of it. I hope you like it. And also I'd like to mention here is, now you have got this displacement stress strain. The plot is here. When you click on edit, you get the data, stress, strain on the left, and the stress on the right. So if you copy this data, you can put it in the Excel sheet and you can plot it there also. So there are multiple ways of doing it. So for now, I hope this is very clear to you. That's how we can simulate some experimental tests in our FE softwares. Thank you so much for your patience. Thank you. Bye.